Hello everyone. So this is the Marais Mathematics Competition, Session B, problem number 3. So you may pause this video and try to solve this problem before you watch the solution. Now here we go. Let G be a finite simple graph, and let K be the largest number of vertices of any clique in G. So we let G equals to VE, where the number of vertices we suppose is Bn. And suppose that we label each vertex of G with a non-negative real number so that the sum of all such labels is 1. So we suppose we label those vertices with A1, A2 to AN. We have AI greater than or equal to 0 for I in 1 to n, and we have the sum of AI is equals to 1. Now define the value of an edge to be the product of the labels of the two vertices at its ends. So if E is inside the set of edges which has the two endpoints are A1 and A2, we have the value of E is equals to A1 times A2. Now define the value of labeling to be the sum of the values of the edges. So this value of the labeling is actually a value of the graph G is equals to the sum of the value of the edge E, where E is in the edge set of G. Now prove that the maximum possible value of a labeling of G is K minus 1 over 2K. Okay, now we want to take a look what is this K. The K is the largest number of vertices of any clique in G. And a clique in a graph is a set of vertices in which any two are connected by an edge. So this means that I have the KK is a subgraph of G, but for all A greater than or equal to 1, which A is an integer, we have that the complete K plus A, is not the subgraph of G. Okay, from this definition of clique, we suggest to see the special case when G is equals to complete graph. Since you have the number of vertices of G is n, so we let G equals to Kn. Then we want to prove that the value of G, because the number of clique is the number of vertices in the clique of G, where G is a complete graph of size n, is actually n. So we suppose to prove this value of G, the maximum is n minus 1 over 2n. So let this be our first lemma, and here's our proof. Now we want to see what is value of G. Now value of G is actually, we write it as above first. Since E, every edges possible in a graph G with n vertices is inside the complete graph with n vertices, so we might write this summation to be from 1 ij till n of ai times aj. Now we want to prove that this value is lesser than equal to n minus 1 over 2n. Looking at this inequality, we suppose to use arithmetic and geometric mean. Since ai to a1 up until an is greater than or equal to 0, which is the non-negative real number, we can use this arithmetic and geometric mean. Or just simply say that since ai minus aj, or since ai minus aj squared is greater than or equal to 0, simplify this, we obtain ai squared plus aj squared greater than or equal to 2ai aj. We can also write this inequality of a summation of I lesser than j from 1 to n in the both side of the inequality. Therefore, we have this expression over here. Now, we should just to add the sum of 2ai aj to the both side, so that in the left hand side we'll obtain something like if I have the sum from ai squared from I to n, then I plus the sum of 2ai aj, which ij varies from 1 to n. I might have a1 plus a2 till an squared. So this is what I want. So first, I might want to simplify the left hand side to be the expression over here. So let's remove this one first. So the expression over left, we can simplify it, become this from I equals to 1 to n. We see for every I from 1 to n, ai squared actually occurs n minus 1 times in the left hand side. So we might write this, the left hand side expression. And for the right hand side, it stays the same. We just drag the 2 outside here, over here. So now by adding n minus 1 times the sum of aiaj, 2 times sum of aiaj to both sides, we obtain the left hand side become n minus 1 times what we want just now, plus a2 until an squared is greater than or equal to, on the left hand side we now have 2 plus 2 times n minus 1 of the sum 1 I j and aiaj. Now we know that this is equals to 1 from the problem, so on the left hand side we become n minus 1 greater than or equal to the expression over here should be 2n, and the expression over here is just the value of g. So now we have n minus 1 over 2n greater than or equal to the value of g, where the equality holds when a1 equals to a2 up and so forth until an equals to 1 over n. You can verify this, that this is the correct configuration. So we have proved our first lemma. Now, if we take a look at a random vertex V inside G without the K click, which is the subset of G, since K plus 1 is not the subset of G, there exists at least one U in the KK, which is the subset of G, such that the vertex UV is not in the edge set of G. Now we want to define the vertex contraction, which we define by G divides UV be the graph obtained by contracting vertex U and V. So we might suggest, we might define how will the label be after we contracting these two vertices. So let P and Q be the label of vertex U and V respectively. Now we contract U and V to a new vertex W, where W has a label P plus Q. And why is the set of neighbors of W? We might suggest that if N of U, N of V be the sets of neighbors of U and V, U and V in G. So the normal N U and N V is the set of neighbors of U and V in G. Now we define N prime W be the set of neighbors of W in G after we contract the U and V. Where should be with the property M prime of W, we might want it to be the N of U union with the N of V. Okay. So now what should be happening to the sum of the value of G? So take a look at the value of G is equals to the sum of every edge in E of value of E, or we might separate it in two ways, where we want to count out the value where is neighbor of U and V. So P times AI, where AI is the subset, AI is the element of neighborhood of U, plus the sum of Q, AJ is the sum of the AJ is the neighborhood of V, plus some value over here, we let it be a big A. Okay, so this value is of course lesser than or equal to A, plus if I have AI is the element of neighborhood of W in the new graph, plus AJ is the neighborhood of W also from the new graph. Why is it lesser than or equal to? Because we have AI greater than or equal to 0 for our I. This is only just an immediate implication of this. So now we have A plus AI in n prime W P plus Q times AI. This P plus Q is actually the label of W. Okay, so now what is A? Now A is the sum of the value of labeling where there is no edges, that is U, that is incident to U or V. So besides U and V, all this, the sum A is the sum of all the edges in E that has no endpoints on U and V. So the summation over here is actually equals to the value of G after we contract it with UV. Okay, and whenever G if we let the G prime is equals to G contract UV, whenever we have G without KK is not empty, we can always find a way to maximize the value of G. i.e., the value of G is equals to the value of G contract with UV. Sorry, this is lesser than or equal to. This is also lesser than or equal to the value of G contract with UV, and we contract another set, for example, it is S and T, and so forth, we might end up with the value of kk, which is equals to k minus 1 over 2k, where if kk contains vertices with labels a1, a2 until ak, the equality holds when a1 equals to a2 equals to so forth until ak equals to 1 over k, and ak plus 1 equals to ak plus 2 until an equals to 0. You can check that this configuration make us have the value of g is equals to k minus 1 over 2k. Thus, we have proved this problem, and thank you for watching this video. Please subscribe or like this video.